Hi, this is Barry Givens, and in this video, I want to talk about the difference between showing that two spaces are homeomorphic versus showing that two spaces are not homeomorphic. So to start off, to show that two spaces are homeomorphic, well, the definition of homeomorphism is that there exists a homeomorphism between the two spaces. So it's an existence style proof. That means to show that two spaces are homeomorphic, you just have to give an example of a function, which is a homeomorphism. So you just have to find a function, or sometimes you might use the fact that homeomorphism is transitive. So you might already know, like, well, these two spaces are homeomorphic and these two spaces are homeomorphic. And so therefore the first and the third are homeomorphic. But in general, it's pretty straightforward to show two spaces are homeomorphic. You just have to either explain what the function is or define the function or somehow describe a function and then make an argument that it is continuous and has continuous inverse and that it's a bijection. Now, to show that two spaces are not homeomorphic, that means we have to show that there does not exist a homeomorphism. That's the negation of the property. There does not exist a homeomorphism. Showing non-existence is harder than showing existence, right? To show existence, you just have to give an example. To show non-existence, you have to, it's just more complicated, okay? So that is logically equivalent to saying that you have to show that for every f, if f is a function from x to y, then it is not a homeomorphism. And again, we're trying to prove a negative there. We're trying to prove that if you just take an arbitrary unknown function, that it's not a homeomorphism. So the way we'll normally do that is by saying, assume you have a homeomorphism and then get a contradiction. So show that it's basically proof by contradiction, that if x were homeomorphic to y, you would get a contradiction out of that. So let's see an example of how we would do that. Okay, here's an example. Let's say that x goes from the reals with the particular point topology with the point p equaling 0 to y equals r with the standard topology. And I claim that those are not homeomorphic. Those are not topologically equivalent. Okay? To do this, what I will do is I will assume they are. So assume for contradiction, for the sake of contradiction, that x is homeomorphic to y. Assume they are homeomorphic. So that means that there is a homeomorphism. There is a function that shows us that they're homeomorphic. And I need to somehow get a contradiction out of this. So I can start thinking about what the open sets look like in each space, what kinds of properties each space has. And I want to show that there's going to be some kind of property or the existence of some kind of set which will show me that they can't be the same. Okay. And for X, we know that that topology, I mean, it certainly seems different than the standard topology, right? In the standard topology, open intervals are the open sets. So the basic open sets are open intervals. In the particular point topology, the basic open sets are sets that contain the point 0. Okay, so like the set of all even integers would be open because 0 is in it. The set of all positive numbers would not be open because 0 is not in it. And so with that topology, the definition of open is very different than the reals with the standard topology. But still, I need to find like a specific counterexample. So I think maybe I want to really focus on the number 0 because that's like a special point for the particular point topology. And I know that, whatever x looks like, I mean, I know what x looks like, it's the reals, but I don't know, like its topology is sort of wacky. Okay. Y is also the reals. And this point 0 is kind of special. Because f is a bijection, there's exactly one point in y that corresponds with the point 0. So I don't know if f of 0 equals 0 or f of 0 equals 9 or f of 0 equals pi squared over 6, right? F of 0 could be anything, but it's something, okay? So let's just take some point over here, z for 0, okay? So I'm going to let z be f of 0. So I know that z is kind of like the new 0, okay? Z is like the new 0 over in y. And I need to think about kind of what could go wrong with this. So there's a couple different ways I could go. I guess first of all, I could say over on the left, there's a set which is open on the left, but its corresponding set is not open on the right. Or I could go kind of vice versa. There's a set I could find on the right-hand side which is closed, but its corresponding set on the left is not closed. So these are the kinds of contradictions I'm looking for. Let's start with the set on the right. Now, singleton 0 is open in X because the definition of being open in the particular point topology is that you're open if and only if you contain the point 0. And singleton 0 certainly does contain the point 0. But if I look at its image, the image of f of 0, that's f of all things that are in that set, would be singleton z. Is that open on the right? No, singletons are not open in the standard topology. Okay, so the set singleton 0 is open in X, but the image under F, I don't know what F is at all. All I know is that F is a homeomorphism, but the image of singleton 0 is not open in Y. I should say Y right here instead of saying in R, in Y. And so that means that there's an open set, but F of that open set is not open. That means that F is not a homeomorphism. Homeomorphisms have to take open sets to open sets, closed sets to closed sets. Pre-images of open sets have to be open and pre-images of closed sets have to be closed. And so this means that F is not a homeomorphism. Which is a contradiction. Okay, so X is not homeomorphic to Y because I assumed they were homeomorphic and then I got a contradiction. All right, so that is the standard method for showing that two spaces are not homeomorphic. What you can kind of see there is that what we focused on was that there was a type of point in X, there was a type of set in X that we couldn't get that same type of set in Y. So the set that it was a singleton set, which was an open set. Okay. In the standard topology, singleton sets are never open. But in the particular point topology, there is a singleton set that is open. And so I would say that that is a topological invariant, that a topological invariant is some kind of property that if one space has the property and another space does not have the property, then they can't be homeomorphic. So that leads us to kind of the second way, the second main way that's really just like a abstraction of the first way. So to show that two spaces are not homeomorphic, the first way I've shown you is assume they are homeomorphic and get a contradiction. The second way is to look at topological invariance, topological invariance. So a topological invariant is a property that is preserved by homeomorphisms. So it's a property that if you have two spaces that are homeomorphic, they either both have to have the property or they both have to not have the property. Okay? Some examples of topological invariance would be like the cardinality of a set. Like if two sets are homeomorphic and one of them has 5 elements, then the other one also has 5 elements. Or if one of them is countably infinite, then the other one is countably infinite. If one of them is uncountable, then the other one is uncountable. Two spaces that are homeomorphic have to have the same size. And that's just purely because homeomorphisms are bijections. It doesn't even use continuity. Okay? Also, the number of open, closed, or sets that are both open and closed is a topological invariant. Okay, so for example, the trivial topology only has 2 open sets, and the discrete topology has way more than 2 open sets in most cases. And so in general, the discrete topology and the trivial topology are not homeomorphic because they have different numbers of open sets. Or in the example that we just saw with the particular point topology, the particular point topology has a closed set which has just one element. Sorry, I said that backwards. The particular point topology has an open set with just one element, but the standard topology does not have an open set with just one element. And so that is going to be a topological invariant, having an open set that contains just one element. And since one space had that and the other space didn't, that tells you they can't be homeomorphic. Another property that we learned early on this semester is the property of being Hausdorff. If two spaces are homeomorphic, if one is Hausdorff, then the other one has to be Hausdorff. So if you have two spaces where one is and one isn't, then you know right away that they're not homeomorphic. Some properties that aren't invariants is like anything that talks about distances, distance between points. For example, when we talked about the surface of a cube and the surface of a sphere, um, the distances from like one side of a cube to the other versus the distances from one side of a sphere to the other, those are very different from each other, but distance is not a topological property. So you can have like crazy things going on with distances, but that doesn't matter. Or, for example, whether or not a set, like as a subspace of R, is bounded or unbounded, that topologically does not matter. Okay? So finally, as an example, let's show that R with the lower limit topology is not the same as R with the standard topology. And there's a few ways we can do this, but I think what I'll say is that the topological space R with the lower limit topology, it has some non-trivial proper subsets that are both closed and open. So what we've seen earlier this year is that this set 0, 1, including 0 but not including 1, this is an open set in the lower limit topology, but it's also a closed set in the lower limit topology. So this set is both closed and open. And R, with the standard topology, the only sets that are both closed and open in R are the whole space and the empty set. That's something we haven't actually shown yet, but if you believe me on that for now, then that we can just go with it, and later on we'll see for sure why that's true. And so R with the lower limit topology has at least one set that is both closed and open, other than the whole space and the empty set. But R doesn't have any such sets, and so they can't be homeomorphic. And in fact, I've written this wrong. R with the lower limit topology is not homeomorphic to R. Okay, so the concept of a topological invariant is going to become extremely important. And as we're learning new properties of topologies, we're going to be really focusing on, is this property a topological invariant? And if so, how can we use it to learn more about what spaces are homeomorphic to what other spaces? All right, thank you for listening.